What I'm going to tell you about is how generic programming and C++ portability give great performance and knowledge of what performs well. It's a very long title, but you will see that we're going to go over it quickly. So, my name is Eduardo Madrid. I am presenting work continuing from something that Scott, Bruce, and I started 2 years ago. A quick introduction for those of you who have not seen me before. I am author of open source libraries. Formerly, I was either a team or tech lead at Snap Incorporated, the maker of Snapchat, or systematic trading hedge funds and other job positions. I am a frequent presenter at these conferences. So if you ever want to follow up on things that I talk about in my presentations, the natural place would be at these conferences. I'm very happy to talk to you about those things. Okay, in this presentation, we're going to continue work from my presentation at CppNow last year, a year ago, on rehashing hash tables and associative containers. They mutually complement. You don't need to watch both of them. You can watch either or none, but you're here, so if you take interest in some topics that I mentioned today, probably there's going to be a complement on the presentation a year ago. I am not going to be using benchmarking to discuss performance, and the reason is going to become clear at 2/3 into the presentation. No code. I'm going to make emphasis on the principles. This is C++ now. I think that it is a more fundamental type of conference than, for example, C++ CppCon. I'm going to bring to you examples that are obvious. Don't be fooled by how obvious the examples are, because they have subtlety that I want you to pick up, and so help me with that. I don't bring the magic that Scott Bruce might have brought to it. That's unfortunate that we don't have him as a collaborator at the moment, but that's the way it is. Okay, this is basically the structure of the topic of today, okay? The white arrows represent improves or gets benefited from. So it is very clear that there is a virtuous loop between performance and knowledge of what performs well. That doesn't need explanation. And we're going to talk about the other arrows in the diagram. It's very simple, nothing that strains the intellect at the moment. How generic programming helps performance? The most obvious way is that it allows the compiler to perform lots of micro-optimizations that other programming languages and other ways of doing programming won't allow for. However, I want us to go back to a very critical example, because it has a lot of wisdom into it, which is to compare the algorithm in the standard library of sorting, standard sort, with the C library qsort, okay? And let's see what we can learn that we haven't learned yet. Obviously, standard sort has much better performance, okay? And I invite you to run performance comparisons in any way that you want, and you'll see that the performance of a standard sort is there. And I don't know if you have picked on this, but it supports any random access container to perform the sorting on it, okay? In particular, for example, a double-ended queue, which is a nice structure that I have used in practice many times before. Qsort is constrained to only do the sorting work on an array. Also, one problem that you have with Qsort is that you require that your elements, the ones that you're going to be sorting, are trivially copyable, because all that you are going to be describing those elements with is the size that they have, right? That's all that Qsort allows you to express. In C++, well, you pick on the comparison operator of the element type of the container if you don't explicitly set what is the comparison operation. What I want to surface for you is that standard sort is undoubtedly, objectively, much better than CQ sort. But what is it that makes it better? I believe that what makes it better is that it relies on the concepts that I'm listing in the slide of comparability, copyability, movability, and the whole conceptualization of iterators that began with Alexander Stepanov work. Without these concepts and the adherence of these concepts by the C++ components that we use, then we would require lots and lots of parameters to provide to something that pretends to be generic, and the performance will never be there either. So, hammering on the point, if it is not clear already, qsort has no concept of element comparability, so you have to provide a function for it. A standard sort, like I said, can pick the one that the element has automatically or allow you to specify one. It is committed to a data structure, which is the array, because it doesn't have any other way to describe data structures. Only supports trivially copyable types. And to top that off, it leaves the compiler blind. C is a programming language that is very popular. People like that the code is always easy to read, but the semantics of what you read in the code is probably too simple, and then there's a lot of things missing, and the compiler is also blind to that semantics. So it puts you in the same position. Therefore, it is a double bad. But anyway, let's go for a quick digression that I want to dispel, because I have talked to a lot of colleagues that they have the fear that if they make very complicated templates, then the compiler is going to do crazy things with those templates and generate, for example, bloated binary object code or inefficient code or anything of the sort, okay? And I'm going to call upon my example from CppCon on 2019 about my presentation about SWAR techniques. I showed you several years ago a technique of divide and conquer that led to an implementation of an important calculation using recursion on templates. And apparently, a lot of my colleagues said, no, that's going to compile to something efficient. Not only it compiled to something efficient, but the compiler was so aware of what was going on that it did auto-vectorization and automatically unrolled the loop to multiply the performance of that very critical loop that I was doing benchmarking by a factor of 20 over what I expected, which was to invoke a platform intrinsic of population count.
Can you say what SWAR stands for?
Yes, SIMD within a register, okay? That doesn't tell you much, right? At the end, I'm going to have the opportunity to go back to any of the topics that interested you, okay? That's one of the reasons why the presentation is purposely short. And we're going to go back to SWAR, okay? Thank you for the question. And by the way, feel free to ask, especially if you're not understanding. Okay. We're going to go back to this link if we have the opportunity and you guys want to do it. All right. So let's move away from the very obvious to something less obvious, okay? One of the benefits of generic programming, which is, well, let's define it in a intuitive sense, what we normally call as templates in C++, is that it forces us, it railroads us as programmers into situations on one size fits all, or to have to be forced to use a particular mechanism, a particular data structure, a particular algorithm, because the way to express, no, my thing requires something different, is not there. Including, for example, when you have your types, and your hypes type have a beautiful move or copy operations, or they don't want to have, for example, a copy operation. We're going to hammer on that example momentarily. And one example of that failure of design is, in my opinion, the design of a standard function. And what I'm going to is that in the very many ways in which we might want trampolines, because what technically a standard function is a trampoline, something that you jump to with the intention to jump further somewhere else, which is the target of the trampoline. It forces you to commit to only one set of choices, and there are other choices that make sense. Not only the ones related to the internal size and alignment of the buffer to hold the targets of the trampoline, but for example, it requires copyability. So to eliminate this restriction or to eliminate this imposition on the programmer, this railroading, big teams like, for example, Facebook's Folly implemented a version of function that doesn't have that requirement. So the other problem that this thing has is that preventively it forces programmers to try to not mess with what the language or the library doesn't support, and that distorts the design arbitrarily backward to its very modeling and conception phase. Like I have seen many programmers that, because they want to do something that sorts, a container that's going to be sorting, instead of having the container of the elements, they have a container of pointers to the elements, so that they know that they're going to be able to sort. But that not only introduces performance penalties, but it's also a busy work activity that introduces mistakes and increases the work to be done. So, yes?
Wait, sorry, maybe I missed this. Could you explain what the second bullet point was referring to on the previous slide? Yeah, it says the actual internal buffer size and alignment.
Yes. So, let's say, for example, that you want a type, which is a trampoline, that is going to hold its targets and is guaranteed to never allocate, okay? Because you know that the types you're going to be feeding to it always have a reasonable size that will make it so if the internal size of the trampoline is suitable, it will not have to allocate, okay? That's desirable. Do we agree with that? Well, there is absolutely no way to express that with the design of a standard function that we have today, okay? Like, you cannot tell it, I want my internal buffer the size of, let's say, for example, say 48 bytes, because I know that all of my trampolines, all of the targets are going to be at most 48 bytes in size. And then what are you going to do? You typically are going to construct a wrapper that has some allocation in some memory arena or whatever, that it is fine to keep it so that you can hold things that are larger than what the internal, well, as a matter of fact, the internal size and alignment of the buffer in a standard function is not even available to the programmer, okay? You cannot know, you are not allowed to know what is the implementation parameters, what the implementation parameters are going to give you. Thank you very much for your question. Do I need to repeat it, Ezra?
We have mics.
Okay. So moving on from the less obvious, the example of what you asked, by the way, may I know your name?
William.
William is a very good, because ever since a standard function, well, even before, when Boost function was incorporated into Boost, there has always been a bike-sharing discussion on what are the true sizes for the alignment and the internal buffer for them, okay? And that continues on until even today. There is a famous blog post by Arthur O'Dwyer that I always cite that shows you the design, it's called the design space of a standard function like components. And there are so many of them. And there are proposals for almost all of them. But again, we are, we say it in Spanish, we're attempting to kill an ass by clicking on it once at a time. It won't work, because what we need is to build superior concepts to incorporate the needs that we have. And by the way, I'm proud that I have done that, and yes, I'm not going to say that the thing is, the problem is not the problem is not solved, because I already produced one of those solutions. And what I did again was to conceptualize the multiple things that participate on a trampoline, the whole arbitrary targets, and I'm very, very satisfied with the solution. Okay, so that's a little less obvious. Now, I think that the most important way in which I think generic programming helps performance is that it allows the systematic exploration of performance-sensitive choices. Now, the thing is that performance of a real application is complex phenomena. And by complexity here, I mean that if you try to isolate, to measure things individually, you're going to have results that very probably are going to be very different to the results of putting everything together into something that does something practical and real, okay? That's the complexity of it, because if it would be just a matter of isolating every component, measuring it independently, and seeing what is the one that performs best, and make the combination of the best individual performers, you're not going to get the best combination performance, all right? And the reason for why we don't have that easy composability, why we have that complexity, is because of the interaction between choices. So let's look a little deeper into those interactions. And I'm going to record to an hypothetical example. Let's say that you have a calculation function, something that has an input that doesn't vary too much. Like let's say that it has only 1,000 different inputs, and calculates and produces an output. One thing that it is very popular, sometimes it works, is to construct a pre-computed table lookup in which you put, has an index, each potential input, and in the table, at each index, you have the result of the function, okay? Like even memoization techniques help you with that. So you have that option of doing the computation, or the option of recurring to a lookup table. So maybe you're going to benchmark and see that your lookup table is 20% faster than the computation. This is realistic, by the way. This is hypothetical, but inspired from a realistic example that happened to me. And then you put that choice into your application, and results that you see that it is, on the whole, 5% slower. So it's very easy to see why this might happen. If the application itself has some component in it that is thrashing the memory, then it is thrashing the performance of the lookup table as well. So you have an interaction, and the net performance drops. So a generalization of what I just described is that the performance boosting resources in processors, I am talking about the caches, the execution units, the decoding ports, the pipelines, the branch predictor slots, which is something that gets forgotten quite often. They are not infinite. Sorry for the double negation. They are finite. So when we do micro-benchmarking, for very sound reasons, because we want to test things in isolation first, what we end up doing is to simulate that those performance boosting resources are infinite, because our benchmark typically cannot exhaust the capabilities of those things, especially if our benchmarks are relatively simple or naive. So we get misleading results. And if you have the interest, we can go back to misleading benchmark results that I have presented in public before. so that you can go back to the presentation and see more how I explain them in the context. At CppCon 2020, when discussing the performance of implementations of type erasure, I showed you guys how the predictability of the trampoline target has a massive effect on the performance of about an order of magnitude, 10 times, 20 times perhaps. And an order of magnitude difference in performance has qualitative implications. Your code is must be different because it is qualitatively different. So in particular, one of the things that I showed you is that compared to my implementation in particular, if the target of the trampoline is highly unpredictable, it really doesn't matter the optimizations that I put in, or the way that I eliminated the inefficiencies, to be more precise, the way that I eliminated the inefficiencies of the normal implementations of function are not very, very relevant, because there's going to be a massive performance hit due to the branch misprediction, okay? But my implementation allows you to do something else while you're waiting for the branch misprediction to be resolved, which is, for example, to improve performance by, instead of having, let's say, 5 arguments in the function call, you do an encoding an encoding of 5 parameters into a single parameter, and on the other side, the decoding of the 5 parameters from the one that gets passed across the indirect jump. That normally would be counterproductive, because in the most critical point of your most performance critical part of the code, you are introducing expensive computations. But if you know that there's going to be lots of unpredictability with regard to the target of the trampoline, then you know that the processor is going to be idle, and there is the opportunity to fit in something that will pay for itself. So, at this point, I don't have the hard evidence of having run the systematic exploration of all the configuration parameters that I have for the Robin Hood hash table implementation that I have been working on for 2 years. But my hunch is that that systematic exploration of the performance choices, sets of performance choices, is going to be the one that is going to push it over the capabilities of competing hash table implementations. Like in the call for the presentation, I was mentioning the specific example of multiplication. In my implementation of Robin Hood hash tables, multiplication is by far the most important operation, because it is used in the critical places. And I have ways to reduce the number of multiplications if I feel that that is throttling my whole performance down, or I have ways to multiply at will if that is not a problem. Let me give you just one example. In my Robin Hood hash table implementation, the sizes of the metadata, for example, what I devote to something called the probe sequence length, can be 3 bits, 4 bits, 5 bits. It is just a template parameter, as well as the number of bits that I hoist from the hash code of every key to the metadata. And that combination can have 8 bits, 16 bits, 32 bits, powers of 2, and we get really good performance. But we have also experimented with sizes that are not powers of 2. And the problem with sizes that are not powers of 2 is that every time that you're going to have to do a computation of an index or so on, you're going to have to do a multiplication, okay? Underneath, like a division by a number that is not a power of 2, it gets converted into a multiplication by the reciprocal, and something similar happens to the residue of division. So we put a lot of pressure into multiplication. That's why yesterday, when I was discussing with my friend here, Fedor Picos, thank you for coming, Fedor. I hope that you're not wasting your time. I was telling him that I haven't seen processors whose execution units have more than one multiplication throughput, or the throughput of one multiplication per clock, okay? They might have processors that have 2 execution units that each have a throughput of 1 multiplication per clock. But 2 multiplications per clock have yet to see it. Okay, so recapping, how generic programming helps performance. 3 levels. The most obvious is because you are letting the compiler have visibility in depth of what's going on. And it can do interesting stuff. And those micro-optimizations are valuable. Number 2, because it makes you make performance-sensitive choices, all right? Like there's a very big difference between having a trampoline that you won't ever allocate to sometimes having to incur the delays of having an allocation, especially in a multi-threaded environment, okay? That has contention on the allocator, for example. And most importantly, because it allows you to deal with the problem of interaction between performance-sensitive choices. For this, you have to have a very robust mechanism to express your performance-sensitive choices.
So if I understand the third point, it's mostly about what you might call policy-based design, like template arguments that don't really change the inputs or the outputs, but just the performance or the implementation of the algorithm or the component.
Yes.
Right. And I think one challenge that I sometimes have is that sometimes I write a component that maybe uses a few subcomponents, and each of the subcomponents is templated on various policies. And I attempted to expose all of them out of my component. It gets viral. Right? So many nodes and so many different tweaks that go all the way up to my main function. And so everything is exposed. It's easy to explore the shape, but my code gets very complicated with all those separate arguments. So can you speak a little bit about that? Maybe?
Yes. Thank you very much for your question. I'm going to tell you something that hopefully is going to be interesting to you. What is your name?
Roy.
Roy. Yesterday, I was talking to Nina Ranz, that works at Bloomberg, and she's doing work on something that is called allocator-aware containers, okay? And what it is happening there is exactly the scenario that you're describing, okay? Let's say, for example, that you have a variant type, all right? The variant type, of course, in the design, normally, will be able to put inside of it any type that you want in the list of alternatives. That's not a problem, without allocations. But what if one of the possible alternatives is a vector of something that might allocate? You might want both the vector to use that allocator and the types in the vector to use the allocator that you want to provide at the top level of the variant. But hello, variant doesn't have that capability of injecting the allocator to the types that are going to be supporting inside, all right? So as far as I understand, because the light bulb went on me just yesterday talking to her, that's what they meant by allocator awareness, that they're just solving this one example of type injection. But I believe that the solution lies on realizing that what is required in this case is a more powerful conceptualization of containers so that they can inject into the part of the container that I call value manager policies that are going to be used by the by the managed values. Did I explain something that makes sense to the public? Roy, did you understand what I explained?
I think so.
Do you
Okay.
mean the allocator becomes part of the typing already, right?
Yes, somehow the allocator needs to become part of the definition of the type of the variant, okay? But not explicitly, because if it becomes explicitly, then you're just going to have a bunch of unrelated template parameters that are going to be confusing as hell. So that's why I'm advocating that you have to re-examine the whole thing and have a more powerful conceptualization. I said the word conceptualization, and I have not tell you what they mean. Jody?
Can I suggest how I solve that, or how I try to solve
Please,
that? So in the past, like we've always built these types with policies, and they all have specific policies. I have a class, it has 2 different policies, so I give it 2 type parameters, one for each one. What I've changed to do is any class that uses policies or types that dictate implementation, they take just a pack. They just take a pack, and it determines, it looks through the pack to figure out what things it's interested in. And then it just passes the pack to all the other stuff down below. And if every class that depends on policies just takes a pack and just uses some metaprogramming to determine which parts of that are things I'm interested in and pull them out and just ignore the others, then it makes it pretty easy actually then I just pass a pack of policies to this thing, and it passes it to anything else, and they can all just pull them all out and determine how they need to go.
There are some limitations in that. So with these slotless policies, I was actually just revisiting this for writing second edition of my book on design patterns. But just revisiting the slotless policies, there are some limitations. Some are coming from the core language, some just, like for example, you can't declare a friendly parameter back. Somebody brought it up earlier today. You can't friend the parameter back. It won't be a way.
I believe that you can, because I believe I have done precisely that thing.
No.
But you mean to befriend the entirety of parameter pack? I think it is possible, but that you befriend a parameter pack and then that makes you a friend of each of the individual members in the pack?
Yeah.
Well,
basically, to friend your policies, all of your policies.
Okay. Yes. So it's not the pack; it is the individual members of the pack.
Yeah. So, but slotless policies solve a lot of problems as long as you're not too slot specific. There are some places where you can't do it, or it's very difficult to do because or you end up basically repeating a lot of things all the time, because sometimes you have expectations on slots that they must provide. Like this slot must provide certain things this way or that way.
Yeah, and then you end up having to, if you're dependent upon a component that has some special thing, then you have to write a meta function that will take your stuff and translate it for it so that you can pass it what it needs.
Guys, let me interrupt you for a moment. The conversation that they're having is truly interesting, but does it need translation? Do you guys need me to explain what they're saying? Maybe not. Go on.
There is an interesting alternative to it, which is you can flip it around, you can do stackable adapters. Where instead of saying, like, my class of policy, policy, which is slotless, you can do add this, to add this, to add this, to add this, to the base which has almost nothing. And like if you're doing is like adding features, then that's easier than doing the whole back.
Yeah. So with things like
Jody, I had to interrupt you because we have members of the audience.
Oh yeah, sure, sorry.
Can I request a translation?
Okay. Maybe it is a good that let's watch the video when it comes out, and I would give you like a reference to another presentation that if you're interested in what they were talking about, you're gonna love, and it is something like a Gasper Asman's policy sandwich. Okay. That Gasper Asman is someone who lives in London, I think, or the presentation for sure was at the London C++ users group. And he described a mechanism to have collections of policies and put them together really neatly, all right? Which is part of the problem that Roy was addressing, okay? And what they were discussing between each other has to do with different intricacies about the problems that you run into when you're having collections of unrelated types stuffed in a pack, okay? And one of the things that Fedor mentioned was that for very, very good reasons, you want to befriend all of the members of a parameter pack. If they are your policies, you want to befriend the policies that are members of that parameter pack. You cannot do that, not outright. But again, Gasperas-Mann's sandwich is the solution to that, because what he does is that he wraps every policy and he constructs a sandwich by inheriting from a base class, and the wrappers inherit from each other, and then you can make it so that the wrapper is a friend of the policy, and the sandwich is a friend of each of the individual ingredients in the sandwich. So you have the solution for the problem that you were describing. But yes, that is true that you cannot do it directly. We went way deep, but I'm really happy because that means that.
I also have another question. But,
okay, Roy?
No, it went. I think you might answer it in the next slide. So. Go ahead.
Okay. Systematic exploration of choices. I mentioned the word conceptualization. Let's go back to that. But we had to talk about portability for a moment. In my experience, portability has the same dichotomy that C++ templates give me, okay? The dichotomy is that most of the times it is the same, but also different, all right? And that is the value, because the idea of portability is that the code has the same meaning on each platform, all right? However, you cannot expect that exactly the same meaning gets transported every single time. Sometimes the differences emerge, all right? And that's what makes it interesting. So I'm gonna talk about why that makes it interesting and valuable within the context of improving generic programming. So when we write portable code, most of the code is going to work as is on any platform. So the portability effort is what unlocks the value of that code on all the platforms that you have. And then it is the key to determine where the execution platform makes a difference. And then you can control that by improving your concepts that will give full support to different choices to truly support a particular execution platform. Okay, so let's go back to generic programming, because the way in which the portability might help you is by giving you hints on what you have to improve on the generic programming side. We saw that what generic programming helps is through good concepts, right? If you remember this example of sort, it was the concept of a container, the concept of iterator, and so on, right? I believe that we can call ourselves that we're doing generic programming when we are devising or improving new concepts, or devising new concepts or improving existing ones, not really when we are using them, although using concepts properly is truly a hallmark of good C++ programming, just not generic programming. So I asked you, because I haven't read these outside, despite of the research that I've done, how do we call these things? When we're devising new concepts, do we call that we're conceptualizing? I like, that's the way that I refer to it. Do we refer to a set of concepts as a conceptualization, like a complete theory of the concepts of something related to an aspect of our programming? I think a conceptualization is a good word for it. So generic programming is making better conceptualizations. How are you going to do better conceptualizations? I don't have good recommendations for you other than to try hard. And let's start by what I know that exists. There is Elements of Programming by Alexander Stepanov. The problem is that that book is a brick, okay? It's really formal, and despite of all of my efforts, I didn't see the practical value to it. And I love theoretical dry stuff. Another source is that the standard itself of our language, C++, defines lots of concepts, but mostly has terminology to be able to define the language and define the language and the library, okay? So it doesn't really help you on what is the substance behind them. Finally, we get to something that is more helpful. It's still very mathematically oriented, but you begin to get the hang of it. There is the book From Mathematics to Generic Programming, also by CppNow and his collaborator Daniel Rose. And you begin by replicating the Egyptian multiplication algorithm. And I thought at the beginning that it was like a waste of time, okay? Like, why do I go to something so primitive? And then I realized that the very same Egyptian multiplication algorithm continues to be used today in cryptography, and it is a fundamental principle and a fundamental tool of lots of programming. And this was completely not known to me. And it is precisely the key at the root of a really good concept, which is to take advantage of the associative property of multiplication, and then you know how to do associative self-application on any other mathematical field. So it is generic programming at its best. It is just very mathematically oriented. There is a presentation that I forgot to mention in my slide, which is a presentation about monoids at C++ now a few years ago by Ben Dean, okay? And monoids is already a scary word. Like, I think that most of us don't necessarily have to know what a monoid is, but it is, again, it is taking advantage of the associative property, a mathematical structure that has an operation that has the property of associative is a monoid. Okay. Myself, I have just divided a few concepts, successful ones, but not too many, so I'm not qualified to give you ample guidelines on how to do better conceptualizations. But we know that they can be improved, okay? Last year, I mentioned that I don't like at all of Boost Flat Math. Boost Flat Math is a useful tool, okay? But there's something that I don't like about it, which is it is a container. And I think it doesn't have a right to be a container, because it should take any container that I want and do flat mapping on it. So there's a clear example of a deficiency. Do I need to explain this better? Okay. So normally when you have a collection of elements, let's say in a vector or an array, if you want to search on them absent any other invariant, you just have to make a linear search of the elements, okay? So if you have 1 million elements in the collection, on the average, it's gonna take you 500,000 comparisons to get to the element that you want, right? That's a linear complexity. Now, if you know that the collection is sorted by the key that you're gonna be searching from, then the property of it being sorted, technically speaking, the invariant of sortedness allows you to activate binary search, and you know that for 1 million elements, it's gonna take you on the order of 20 comparisons to be able to reach the key that you're looking for, okay? So you have converted linear complexity into logarithmic complexity by sorting the collection. So, okay, Boost Flat Map is, let's have a container that is gonna maintain the elements in a sorted way, and therefore it's going to give you the logarithmic complexity finding or searching on the keys in the collection, okay? And like I said, that's useful. Why do I object is that Boost Flat Map doesn't have the right to be a container itself. It could be something like a container adapter, like a standard stack that uses any container that has the properties required to implement a stack and gives you the stackness on top of it. You see? Okay.
I have a question. How would you balance something like if this is a container adapter, you can't use all the properties of the container, only the things defined by the concept. If we know it needs to be sorted, I might try to use something like
but I already disagree with your premise.
Then it couldn't use the private, the details outside of the concept.
Why not?
Then what is the concept constraining then?
Well,
Like if an adapter,
I do believe that a stack in particular has that very problem. Okay, and I have seen lots of people, including my former employer of Snap, that we had to re-implement the equivalent of a stack because we could not use move-only elements in them. And a very clear example of move-onliness is things that have threads in them because the threads are not copyable. It is just a waste of effort. So I believe that a better conceptualization would be, okay, I'm going to give you the interface of looking up elements and leave you alone on your own with the underlying container that is going to have the values. As a matter of fact, my very presentation last year is exactly about that. So you see, it fits a lot into what I have already worked from my prior presentation. So, and I constructed this component that I called, very not originally, lookup, and it is an adapter that gives you different types of lookup depending on the underlying implementations that you give it, because you're not going to give it to a lookup a container, all right? You might give it, for example, a sorted container, which is not even its own type. It is the decoration of sorted, saying this container has the property of being sorted. Therefore, the lookup now knows that it can do binary search on it. Okay. Thank you for the question. Your name?
Joe.
Joe. Yes, and an example of a concept that can be improved is what I was telling you moments ago of my conversation with Nina Renza yesterday about we don't have the way to inject policies into containers. Have you heard the phrase, this is an interface that leaks implementation details? Please raise the hand. Excellent, very good. Almost everybody is awake because they raised their hand. All right, then I believe that concepts leak the specifics of the realizations of the concepts. In a similar way as an object-oriented interface leaks implementation details. But also something interesting, or I believe interesting, which is concepts might leak abstractions to their realizations. Let me give you an example of an abstraction leaked from a concept. Standard function, again, has some concept of what a valid target is. And among the properties of that concept is that the target needs to be copyable. And as we discussed before, there is no good reason to require that. So it is an abstraction, the abstraction of copyability that got leaked into the concept of target of a trampoline. All right? Another example is of a bad concept. I have never figured out, not even when I asked this question to Björn Strostrup himself, why standard sort requires random access iteration. Because I went ahead and implemented sorting, the algorithm of quick sort with great performance without requiring random access, with just forward iterators even. So, and that is used in production as far as I know at the flagship product of my former employer to this day, and a very important part. So,
I think the std list, for example, has a member function called sort for that exact reason, because you cannot sort using standard sort. At least you can sort it with a member function. That's one thing. And
I wasn't aware that list has a sort. You know, so this is compounding on the error.
Yeah, exactly. At least I agree with you.
That's right.
I think the motivation was that it could be much slower.
No, that cannot be the motivation, because that's so very simple to metaprogram away.
Does the sort algorithm you implemented satisfy and log n algorithmic complexity?
Of course.
It does. Okay.
Not only that, it guarantees it.
Comparison.
And no memory allocation.
Well, no.
Sort guarantees to not allocate memory.
Quicksort has a memory complexity of the logarithm because it needs a stack. So.
Well, it has a stack. It has a stack, but it doesn't have like an auxiliary array of pointers or anything.
No. You can see my implementation. It is a Su quicksort. Roy again?
No, I'm just saying that stood list also does it with n log n.
Yeah, it's because. Your name? Steven.
So a basic quicksort can be implemented with only forward operations and bidirectional operations, but not every sorting algorithm can be. And the standard does not mandate quicksort specifically. In particular, most sort algorithms today use something called introsort, which is a combination of quicksort and heap sort. Heap sort does require random access to access the heap.
Yes, I would agree
And the
with
reason
you.
it does that is to guarantee worst case behavior. Quicksort is worst case n squared.
Well, you can spice it up, yes, but thank you for your Steve. Thank you for your explanation. The one recommendation that you must exercise in earnest is to improve concepts. Okay, that's gonna be the key for you guys to get more out of the complexity of C++. Improve concepts. Try to identify when a concept is leaking an abstraction or leaking an implementation detail or details of the types. Like one example of how they leak. Let's say that you have a template that uses something like a number, but because it supports arithmetic operations on them, okay? But floating point numbers are weird. Like there is the not a number, and the not a number throws a wrench into many assumptions that you have of what the operations on numbers ought to behave, okay? If your template misbehaves, given those characteristics of a floating point, they are not truly supporting them, okay? So that is a characteristics of your realization, which is, let's say, for example, the double type that you're using, that is leaking into your concept, and it's an opportunity to improve it. Maybe you're gonna use, for example, a fronting, in which you're gonna have some case scenario in which if your type in the template is of a floating point type, then you are gonna do a few operations differently. Okay. Good portability helps identify where the platform details matter, improve the concepts related to the platform details, and then cycle back into better portability. You see, it loops on itself. That is the key. That the more you loop on this, the better your software becomes. Okay, I am just going to give you an overview because the Robin Hood hash tables, I have already covered them at 2 presentations at conferences. And this part is so complex that I am not going to be able to give you the value of explaining each individual part within the parameters of this presentation. But here we go. If you remember your algorithms classes, there is something called open addressing and closed addressing. And the Robin Hood hash tables are those that use closed addressing, meaning that you are not going to be allocating on a bucket can have only so many elements. One moment, Steve. Only so many elements. Well,
I think that's backwards. Open addressing is when you have a flat array and do not allocate.
You might be right, because there is open addressing and
open addressing is when you chain in the same array.
But then you're contradicting Steve.
No. Chain inside the array. You don't create external chains.
You don't do buckets and chains. You're just chaining in the same array.
Yeah.
By indexing.
All right. Well, Robinhood chains within the same array.
Yeah.
Okay. That's why it requires a pre-allocation of an array to work with. Okay. And there are a lot of concepts related to that very fact that are absent from the normal standard map and unordered map, because they use open addressing. Then, because they are hash tables, then there are the concepts related to hash tables, like the hash function itself, the properties of the hash function, and then like what are the transparent types, for example, like the types that if you want to search for a type of that, a value of that type, you don't need to convert that value type to the key type in the hash table as a transparent type. So there are concepts related to that. Then my coworker and I decided to support weak hash functions, poor hash functions. And so we made a set of concepts and implementation choices that were defensive with regards to the user-provided hash function. So, and then are we going to allow our users to have visibility into all of these mechanisms? And we decided to do it. And if we provide visibility, then we had to support them and honor them and consistently provide access and support. Because none of our implementation details, like I was telling you before, the parameter sizes of what we devote to the hoisted, the number of bits for the hoisted hashes, the probe sequence length, the encoding in the metadata, either in blocks or a single array. We had to provide access to that, and all of them require their own concepts. Another thing is, I'd really like to mention the presentation by Michael Skarupke a few years back at CppCon, because he did a very thorough job. And one of the ideas that he introduced in his implementations was a tail of elements of a particular size, so that you don't have to check when you're doing a find that you have reached the end of the array of searching, because the tail guarantees that you're going to terminate before reaching the end. So this is an improvement, but it has some drawbacks. Therefore, we had to provide, it's just another choice that we have, you see? And it has its own set of concepts. We split hashing into 3 parts. The user-provided hash function, of course. Then from the hash code to the slot index is its own way of doing it. It's not fixed. You can do this in a multiplicity of ways. And the way that you're going to do a selection of the user function provided hash code generated bits, how are you going to pick them up to make a representative and hoist them to the metadata? That's another choice. We had a hard commitment to encode the metadata has probe sequence lengths, and hoisted hash code has an heterogeneous collection of elements. And this is not necessarily an array, which spills its own set of concepts. And lately I have been working into structuring everything into cache lines, blocks of 64 bytes, and see how far I can get with it. Another hard commitment that we had from the very beginning is to do the SWAR-based techniques to do finding, but our SWAR is extensible to physical SIMD registers. So there are multiple concepts related to SWAR that have an impact on everything on our implementation of Robinhood.
So are all these concepts you just listed something that is internal to the Robinhood hash table implementation, or are these features that users can choose to opt into or opt
Both.
out of? Both. Okay.
Yes. Because the whole point is that I'm coming to you to advocate for genetic programming on making it so that your software makes it so that all of the reasonable choices can be represented as choices in the code, okay? And believe it or not, that doesn't add complexity. The problem is that when you want to do something useful with all of these extra features, you have the inherent complexity of using them. So the support for choices does not add too much work into what you're doing. But actually using all of those possibilities lead you to all sorts of complications, especially because of the interactions, you see? It's like I was telling you earlier, guys, about multiplications, that if we have 3 ways to work with the key. One is to get the hash code. One is from the hash code to the index, and one is from the hash code to the hoisted bits in the metadata. Okay, how are we going to measure the impact of doing those 3 things separately, as opposed to having only one mechanism that from the hash code gives you the index, and from the index you pull a few bits like the Google people do in their Swiss tables to the metadata, okay? And so they have some problems, and they're satisfied with the solutions that they have provided to those problems when they just copy has bits from a potentially weak or poor user code, user hash function provided hash code, okay? So we have all of that chain of choices and experiments and analysis to do as a possibility, plus all of the choices of following the alternatives. Or by, I think, because it's multiplicative. Okay, I continue to work on the Robinhood implementation, and the work that I have been doing is hopefully interesting. I am happy with, yes, I think there are valuable stuff in it. But my aim has always been to get to production strength. I'm not there yet. Like, for example, I need to learn about prefetching, and I need to finally get to learn SIMD on ARM processors so that I can do the wrappers for SIMD that are not contaminated by my monothematic experience with Intel's SIMD registers, or without prefetching, the performance of my implementation is not going to be there. So if I release something, I have the fear that people are going to benchmark it, trash it, and forget about it for all eternity. So, but anybody who has asked me access to the latest code, I have given it, okay? You just had to ask. And that's an opportunity for me to have a conversation with you that I will, and I'm gonna go over that topic momentarily. We are doing well on time, I think. The epilogue of this presentation. I want to sincerely thank Scott Bruce publicly for all the help that he provided when he was very active in the project. But alas, he took an hiatus that might become permanent. And what we have been doing requires inspiration. And sometimes you earnestly want to contribute, to work on these things, but the inspiration is not there. So it is not something that we can criticize. And of course, that it requires a mountain of work. And unfortunately, Scott is very complicated. He commutes between New York and Los Angeles. He has a very tough, naturally, job. And this is far from his normal job activities, further than, I think further than what it was. So there you go. Then I want to talk to you about, because C++ now is a different type of conference, and it's like closer, like the difference between the presenters and the audience members is very little. Like my friends Jody and Fedor were taking over the presentation at one point, and I really thank you guys for that. So, you know, the reason for why I come to present and why I advocate for you guys to attempt to do it is that even if it is not your job, because it is a very great way to explore good ideas until a decision point that you can make and determine, yes, this is good, or yes, this is not good. And when you get to that determination point, it is valuable either way. There is no recourse but to do the mountain of work to try to explore the viability or the characteristics of a good idea. And unfortunately, obviously, the majority of the ideas are not going to be better than anything done before, but the journey is an exhilarating experience. And then if you do something, you want to communicate that to an audience such as this, because there are going to be interested people on them, okay? It also happens that sometimes, like it happened to me with my SUS type erasure framework, the things get productionized and they get a lot of sponsorship, and then they get new levels of competency and capability. But then also it happens that when something gets adopted, then the work becomes bulkier, and you have to. Edison is right, because most of the good work is 1% inspiration and 99% perspiration. And this is when we hit hard limits. Like you can only do so much, right? And when cooperation becomes really important. Well, I was telling you that to get my Robinhood to production strength, I need to learn SIMD and in the ARM platform, and how to control prefetching, and this includes like how to benchmark things that use prefetching. It's something that I really don't know, and like the number of page swap misses and those things. And to be honest, they are somewhat of a distraction from other higher priorities that I have at the moment. Well, I really thank you for having come, and this is the opportunity to go back to any of the topics if you want at this point. Right.
So I think you touched a little bit on the on a trade-off regarding the early release of open source code, right?
Yes.
If you release too early, maybe people will benchmark it and not be impressed. But if you, on the other hand, maybe others will come and assist you, and you get better collaboration. Mm-hmm. So I wonder if you take on that.
Yes, I did my type erasure framework completely in the open, and got to sparingly help here and there, and that was good. But this is different because I didn't start from attempting to achieve production strength with a type erasure framework. Okay, this was just a pure exploration of how far I could get. This is different. So this is like I have not delivered on what I set out to do yet. Okay, and I believe that it is fine because the timeline is reasonable. And when I'm able to deliver on the premise of something that is production strength, the only problem is that, come on, Martinez's implementation of Robinhood is really good. I believe that my implementation is already a tad better than Maltes Karupke. But Maltes Karupke gave up on Robinhood, did something that he thought was better. I don't share his opinion, and eventually gave up because it was too much work. That's what he put in his public. So I'm getting there, okay? So have faith, I guess. And if you're willing to help, you're very welcome.
So you talked a lot about these generic programming from the standpoint of providing these, I guess we'll use the word policy, these policies for determining behavior. How much work have you done in trying to figure out those policies by introspection of the things that are given to you rather than being provided them directly?
I don't understand given to you.
So when you instantiate your Robinhood, your hash table, or even these just generic types, you're giving it types. You're giving it template arguments to fulfill those template parameters.
Yes.
Right? So you're giving it specific pieces of information. And so you're using those pieces of information to determine how you're going to behave.
Yes.
But you could also use those pieces of information to then introspect the things that you've been given and determine what types of things they support, and then make your decision based on that rather than being told explicitly.
That also happens. Organically, I would say that then I think I understand your question, and the answer is organically. Okay. Because you discovered, that's an excellent question, by the way, Jody. In the process of making better concepts, you discover entirely new concepts that pop up. And then you flesh them out and provide support for them, okay? Some other times, it is very explicitly a requirement that is driving a chain of dependencies and policies that give you the, like, let me give you one example. By the way, guys, when you were talking about, especially when you began to answer the question of how you solve the problem that Roy was asking about the complexity of providing policies, you know that the SU-type ratio framework is entirely based on policies. And I set out to implement support for the policies that I already understood. All right, like in particular, supporting a value in the local buffer versus the potential allocation on the heap, those two flavors of it. But in the process of implementing more sophisticated forms of support for values, then I discovered, hey, I can implement value managers that are aware of concepts related to value orientation or to data orientation. And then they will need their own policies regarding memory arenas and base arrays and scattering of fields and so on. I implemented something called Delegate, which is like an emulation of C#'s Delegate component. And that introduced the complication of you are going to have in a particular space heterogeneous collections of trampolines. So how to support a collection of heterogeneous types gave rise to their own concepts.
Yeah. So, and one comment if I can. So, all the open closed addressing thing that you made a mistake on the slide, it can easily happen because open addressing is also known as closed hashing. Yeah. And so
yes, that was the symmetry that I was attempting to remember.
And the other thing is that there's a few things that I've actually taken from your previous talks. So one of the things is you had actually demonstrated a couple of years ago the importance of preserving registers, because even though compilers should optimize it, they're not necessarily going to do that. So if you have a chain of functions where you're passing things down, and yet they're in different orders in their
different positions in the argument list,
pull out your registers because you're just going to keep swapping them into registers to pass them. And so I implemented basically just.
And you saw benefit.
Yeah. Well, a lot of functions might just have. I take anything, and then you use generic concept to actually figure out what those things should be, but it doesn't matter what order they are, and then it sorts them based on a particular criteria so that all the chains down the line forward all those things, all the parameters using
In a consistent way.
But I was inspired by one of your talks a couple years ago. So you talk about all the work that happens in all these things and you present them. People use stuff that other people present. So it's very beneficial. Even if, as you said, what you end up discovering isn't the best new thing, the process of it does provide things that are of benefit.
Indeed, thank you very much for that comment, Jody. I think that we still have 10 minutes, right? So I think that we can just say goodbye by looking at a little piece of code and a Godbolt output. And it is the link. Oops, I should have made this a link itself. And now I am having a little trouble into the simple copy and pasting. Very quickly, guys. Telescope?
Yeah. Like the physics thing with that's what it does.
I don't see that.
Wi-Fi is something with physicists.
There you go. Oh, there you go.
Well, I am at the hotel, but if it works, it works. All right. So this is not very complicated. The link is there, and I invite you to check it either from the presentation at CppCon in 2019 or when you get the slide from here. That I have the population count to count the number of bits given a size, because you might have a base size of an integer of 64 bits, but you want to count 8 population counts of 8 bits internally, or 16 population counts of 4 bits each, and so on, right?
Do you mind zooming in a little bit?
Yeah, thank you for the request, because I do know that it is difficult to get. I'm not.
You can increase the font size without zooming everything.
There is in the A, you can increase the font size.
Yes, that is absolutely true. It's a superior way of doing it. Okay, this is probably making enough of a difference. Okay, so a population count using logic, meaning computation, is a divide and conquer strategy of calling the population count with half of the bits and adding them together. Okay? So simple, but it is a recursive expression of this little thing here, okay? So there is also the population count using the built-in, which will use the population count instruction in the processor itself. And that's what this thing does. And of course, there is some simple metaprogramming that decides to go to one or the other and so on, but I am calling here them explicitly. And if we go here, like for example, using the built-in, it is just to invoke the population count instruction of the assembler, all right? And here we're gonna see a simple function that I'm going to time it outside of execution, that is going to be doing the counting repeatedly with each of the inputs in the collection, and it's going to consume that result by just using the exclusive OR, so the compiler cannot eliminate any of these away, and returns that, okay? It is actually a sound way of requiring work for the purpose of benchmarking. And if we go the implementation, This, you can trust me on this one. This I traced, and this is the fast path, the path that the compiler is optimizing for, what the compiler assumes is going to happen more often. And even if you don't understand what this thing means, I can explain it to you. In no place whatsoever, this code ever mentions SIMD registers. The source code doesn't mention SIMD registers. However, the compiler went on its own and did auto-vectorization. That's why you see instructions like a VP exclusive OR of XMM registers. And not only that, what it is happening here is that broadcasting from 64 to 256, and then here begins the loop using vectors of 256 bits, and at the same time unrolled forwise. The compiler decided that the best way to implement this was not only to auto-vectorize, but to put 4 iterations at a time in the per loop counter. Okay, so that's what he did. Now, even more surprising to me, I am invoking here the population count built-in, which is the assembler itself. But guess what? The compiler understood that what that population count was doing could be implemented better by using the same trick of auto-vectorization and loop unrolling. Therefore, the net result is that this ugly thing takes about 1/10 of the time that this thing would have taken. Of course, that I know how to manipulate the compilation options so that the auto-vectorization doesn't happen, and I can measure it. So I guess, so I showed you in the last minutes that I have in the presentation, an example of a recursive specification that the compiler had no problem whatsoever to do miraculous things with it. And number two, that even within this source of complications of vectors and so on, the compiler is very happy to even get to the point of substituting an intrinsic on the assembler for what it thinks will execute better by, in this particular example, doing loop unrolling and especially auto-vectorization. Yes. Now I'm really done because my, so thank you very much.
That's a problem.